Hello dear student, I am Monul Islam. Today in this video we are going to discuss 3 questions of PhD interview of Guwahati IIT. Okay, so let's start. First question. Let T from M to R to M to R be defined by T is equal to x plus x transpose. Okay, and x belongs to M to R. Then what is its rank? What is rank of T? Okay, what is nullity T? Nullity T. Okay, and is it transposition linear? Is it linear or not? If it is linear, then find its rank, find nullity. This is the question. Okay, so we are going to solve this question. See, the transformation given by this T from M to R to M to R by Tx equal to x plus x transpose. Okay, then is it linear or not? We check its linearity, and x belongs to M to R. So take two vector x, take two matrix here, x y are matrix. Okay, x y belongs to M to R, means x y are both two positive matrix with entries, real entries, and alpha beta to real number, means scalar. Then T of alpha x plus beta y, this gives ability transposition alpha x plus beta y. Okay, and this gives alpha x plus beta y a transpose. Okay, so this gives alpha x plus beta y, and this gives alpha x transpose plus beta y transpose. Okay, so if you comment this term, this gives alpha x plus s transpose beta y plus y transpose. Okay, so this gives alpha into tx plus beta into ty. Now alpha beta are identity scalar. Okay, and this gives t of alpha s plus beta y imply equal to alpha tx plus beta ty for all x y belongs to M to R, and for all alpha beta belongs to scalar field R. So this gives the transform is linear. Okay, this prove that the transform is linear. So this implies T is linear. Okay, now if it is linear, you can easily find it rank nullity. Okay, so we are going to find it now its rank. Okay, find it rank. Question 1. I am choosing X to be arbitrary matrix, and it is A, B, C, D belongs to M to R. Okay, then what is Tx? Then Tx will be x plus x transpose. Okay, so this gives A, B, C, D. If you take transpose, then A, B, C, D. Okay, so this gives 2A, B plus C, C plus B, 2D. Okay, you can name it like this. You can name it like this: lambda, mu. If it mu, then it's also mu, and it is, you can name it delta. Okay, so you can write this as lambda into 1 0 0. Okay, plus mu into 0 1, sorry 0, it is 1 0 1 0, and delta into 0 0 1. So this matrix belongs to a span of, so this matrix belongs to a span of 1 0 0 0 1 0, this 0 0 1. Okay, now you can easily check this set. If you name it S, say this set is linearly independent. Okay, you can easily check it. So I have taken an arbitrary matrix of M to R, and this matrix is actually span of this vector. Okay, so you can say from here I have taken arbitrary matrix from range space. Okay, you can choose, you have to take from range space of T. So if I take an arbitrary matrix of range from range space, then this implies then the matrix belongs to span of this. Okay, so from here you can say range space of T RT will be, you can say range space RT of the transform T will be span of this three matrix 1 0 0 0 1 0 and 0 0 1. Okay, if you name it S, then range space T will be span of S. Okay, and clearly this set of matrices, these three matrices from a linear set. Okay, so this will be basis, so S will be basis, so S is a basis of range space T. And if it basis, then dimension of range space of T will be number of vector in S. How many vector? A1 to 3, so T 3. So range dimension of S means rank T, so rank T will be 3. So from here I prove that rank T is 3. Okay, rank of the transform is 3. Now if it clear transform and rank is 3, so you can find easily by nullarity by using rank nullarity theorem. We all know rank nullarity theorem. Okay, using rank nullarity theorem, by rank nullarity theorem you can calculate easily it nullarity. Rank T plus nullarity will be dimension V. Dimension V means M2R, and all the M2R dimension is 2 cos 2 means 4. Now rank T is 3, so what is nullarity? Nullarity will be 4 minus 3, so this is 1. So nullarity will be 1. So for the transformation rank T, rank T will be 3 and nullarity will be 1. You can easily find this. If you add this, then this gives 4, and dimension of V will be, dimension V is also 4. So it's okay. So I have described the question now. Okay, this question asked in Guwahati IIT PhD interview. Now we are going to another question. That question is asked in Guwahati PhD interview also. Question number 2. Can you give me an infinite dimensional example of infinite dimensional process? Can you give me an infinite dimensional vector space example? This is the same question. Guwahati IIT interview. Can you give me an infinite dimensional vector space? Okay, so it is best example is if I choose the V is R and field over field is Q. Okay, then V over R, V over F means then this vector space V over F. Okay, V means R over Q. Then this is an example of infinite dimensional vector space. Okay, vector space. This is an important example of infinite dimensional vector space. Okay. Now it is the same question. How you know this vector space infinite dimensional? Can you prove this? Okay, this question was also asked in Guwahati IIT. So if you try to put this, then it's best way to prove it by contradiction. Okay, so I am assuming let dimension R over Q is finite and it is n. Okay, I mean finite. Okay, but now I create a contradiction. How? See, if I choose a consecutive prime, n plus 1 consecutive prime, p1, p2, pn plus 1, these are n plus 1 consecutive prime. Okay, the n plus 1 consecutive prime. If you take this, okay, and if you consider the set this, I am considering the set, let S equal to log p1, log p2, log pn plus, obviously base is E, this set. Then you can prove this easily. This set is linearly independent set of n plus 1 vectors. Okay, Okay, you can prove this easily. This is the set of n plus 1 vector. Okay, because if any two members, suppose these two members are equal, log p1 equal to log p2, this would imply p1 equal to p2. Okay, this is a condition because I have assumed previously that these are n plus 1 positive number. No one should be equal, and no two should be equal. So this set is Lie element. So this set contains n plus 1 vector exactly. Okay, now we are going to prove this set is Lie element. Okay, and this gives our condition. Okay, so how we prove this Lie element? So we have to take it is scalar combination alpha 1 log p1 alpha 2 log p2 alpha n plus 1 log pn plus 1 be 0. Okay, so you can write this summation I equal to 1 to n plus 1 alpha I log pi equal to 0. Okay, so this is a property log. You can take it up by upper side of pi. So if you apply this summation I equal to n plus 1 log pi alpha I equal to 0. Now take exponential on both sides. If you take exponential on both sides, exponential summation I equal to n plus 1 log pi power alpha I will be exponential of 0. And we all know exponential 0 is 1. So this gives 1. Now this will imply this exponential sum. Okay, so you can take it by like this: exponential log p1 alpha 1, exponential log p2 alpha 2, and this exponential log pn plus 1 alpha n plus 1 will be 1. Okay, now exponential log, it will be cancelled, so a term remain this also. Exponential log will be cancelled, so this term will be remain. This in this case this term also will remain. Okay, how you know this? Because we all know the property. This is the property e power log power m. This will be m. Okay, if we apply here this, then this gives p1 power alpha 1, this gives p2 power alpha 2, and this gives pn plus 1 power alpha n plus 1 equal to 1. Okay, now if you think it briefly, then you can easily that alpha 1 alpha 2 alpha plus are 0. This I have left this p1 p2 pn plus 1 p2 alpha 2 and pn plus 1 power alpha plus 1 will be 1, right? Now p1 p2 are prime. Okay, these are prime. Remember this, these are prime. So we all know each prime is greater than 1 for all I equal to 1 to n plus 1. Okay, but their exponent power will be gives 1. Okay, it's when possible. It is possible only when the powers exponents will be 0. It's possible only one case exponents would be 0. Alpha n plus 1, this would be 0. And if this class will be 0, this class will be 0, then it easily imply, and it says from definition, you can say from definition that this set of vector log p1 log p2 log pn plus 1 are from a Lie element set. Okay, so from here you can say log p1, say log p1 log p2 log pn plus 1 from a linearly independent set of n plus 1 vector, and this is the contraction. Okay, because if I assume dimension q over r is n, so maximum linear subset, maximum linear set of vector be n, but in case we find n plus 1 linear set of vector. Okay, so this is never possible, so this gives a contraction. So dimension r over q is never finite. Okay, is not possible. So what is possible? So dimension r over q will be infinite. Okay, so r over q is the infinite of the vector space. So important example of the infinite of the vector space is r over q, and here is the proof that I have proved. Okay, this true question asked in GUWAHATI IIT based interview. Now there is one more question. I am writing that question. It's a very simple and very important, interesting question. Can you say how many homomorphism? How many homomorphism from set of real number R to R exist? From second order to second order, how many linear transform, how many homomorphism or linear transform can we say exist? Okay, how many? What is the number? Can you tell me? It's very easy. Now, suppose f is a from R to R is a homomorphism. Okay. Then what is property? Property imply f of a plus b will be fa plus fb. Okay. For all ab belongs to R, and second property is f of ab will be fa into fb for all a belongs to R. This is not homomorphism, it's a linear transform. Okay, I'm writing it wrong, sorry. It's linear transform. How many linear transforms exist from R to R? From set to set number, how many linear transforms exist? So if it linear transform, then first property will be remain same. F a plus b will be f of a plus fb, and second property is to are different. So I'm rewriting the question. This question was this. Can we say how many linear transformation R from R? How many linear transformation exist? Okay. How many linear transformation from set of real number to set of real number to set of real number can you find? Okay. Say suppose f from R to R be a linear transform. Okay. Then it property imply f of a alpha plus b beta simply a f of alpha plus b f of beta. This is the property of linear transform. Okay, for all a b belongs to scalar field, this will be R in case, and alpha beta is also from R. Okay, this is the property of linear transform. Okay, so if f is a linear transform, then for all R belongs to R, you can write f of R will be like this, f of R into 1. Okay, this is always possible. I am writing R in place of R, I am writing R into 1. Possible. It is homomorphism. You can say it is homomorphism or linear transformation. Okay. Homomorphism. Actually, the question was f from R to R, how many homomorphisms exist? Okay. Homomorphism is also linear transformation. So you can replace it by linear transformation. So f of R, you can write f of R. If it is homomorphism, then you can write this f of 1 into f of R. Or you can say f of R into f of 1. Okay, if f of 1 is a scalar, so name it C. So this gives C into f of R. Okay, so you can write this f of R equal to C into f of R for all R belongs to R. Okay. I have done some mistake for R. No, in this way you can find. See. For all R belongs to R, f of R, you can write this like R into f of 1. Okay. Now if you apply the second property of homomorphism, okay, for the second property of linear transform, this will be f of C into R, C into f of R. Okay. For all C belongs to scalar field F and for all R belongs to R. This is what true. Then if you can take R outside, so you can write this R into f1. Okay, this you can write this into f1. So f1 is scalar, so name it, if you can name it C, so C into R. Okay, but C is f1. Okay, say so f of R will be C into R for all R belongs to R. So all linear transformation from R to R will be of the form this f of R equal to CR. Okay, you can name it y equal to CR, means it's straight line. Straight line from y equal to CR. All linear transformation from R to R will be like this, f of R equal to CR. f of r equal to CR. So if f is a linear transformation from R to R, then it must be of the form f of r equal to C into R for all r belongs to R and C equal to where C is f1. Okay, this is a question. Now from here one more question going to be asked. Okay, this question also asked in some NIT PhD interview, that f is a linear transformation from R to R. Okay, this linear transformation also given that f of 1 is 2, f of 2 is 1. Then this such a linear transformation is possible or not? Such a linear transformation is possible? Possible? Not. Okay, we're going to answer this question. We know if a linear R is if a linear transformation from R to R, this is a linear transformation, then f must be of the form this f of r equal to CR or R belongs to R. Okay, now if we apply the condition f of 1 equal to 2, then this gives 2 into C into 1. This means C is 2. So this transformation will be like this: f of r equal to 2 into R for all r belongs to R. Okay, f of r equal to R. Now if you going to compute f of 2, what is f of 2? F of 2 will be 4. Okay, in this case f of 2 will be 4, but it is given f of 2 is 1. Okay, given f of 2 is 1, you find f of 2 is 4, but it is given f of 2 is 1, so it is a contraction. Okay, so it is a contraction, it is not equal to 1, so it is a contraction. So such a linear transformation is not possible. Okay, so such a linear transformation f from R to R is a linear transformation, and with f of 1 equal to 2 and f of 2 is 1, is linear, such a linear transformation is never possible. It is not a linear transformation. Such a linear transformation is not possible. Okay, but if only one person is given, only this condition is given, f of 1 is 2, then this linear transformation is possible. This linear transformation is this: f of r equal to 2r for r belongs to R. This is the example of this linear transformation. Okay, so thank you. We discussed 3 questions of GUWAHATI PhD interview. In upcoming video we will discuss more questions. Okay, so thank you very much, and please subscribe my channel. So thank you.